it's Dr. Know-It-All. I am yet again with Dr. Scott Walter today. We're going to flip-flop roles just a little bit. In the last video, if you haven't seen it, check it out up here. But he taught me all about robots and robot dating and everything. And today I'm going to talk to you about transformers. So this came out of a conversation that we had just online, like chatting with each other. And I realized that there were some misconceptions that you had about transformers, neural network transformers, specific, not the 1980s toys, but the neural network architecture. And I think it's very valuable for, not to throw you under the bus, but put you in the place of an everyman who is smart and well educated, but doesn't know this specific topic particularly well. And we're going to go back to the classic paper from Google from 2017, which is just barely over 5 years ago. It was December of 2017, which is just blows my mind that it's only 5 years ago that this whole thing started. Yeah. First of all, welcome. Thank you for joining me. And
Thank you also.
Did you want to I guess you said you wanted to kind of go through your understanding of it first, or maybe you could tell me before your understanding of it before we had the chat.
Yes. So my understanding, my misconception, which we're sort of assuming might be a similar misconception out there, or maybe I'm the only one who really didn't get it. So I think part of it, what prompted me to do this, is that there was a really good paper by Stephen Wolfram explaining how ChatGPT works. And Dave Lee ended up taking that and then asked for a summary. And I looked at the summary, and there was like one aspect of the summary I wasn't sure, because we know that it can fabricate and get some facts wrong here and there and make things up. And I was just kind of wondering, is it a little bit off on the summary? Because it was talking about the transformers and then how the transformers are used to teach it, I think, with like a large data set. And that was like, I didn't think that was the way it was. So this is like my understanding, is that a neural network is, as we know, is a very complicated network with all these weights that you've got to adjust. And by using the process of back propagation and some calculus and a few other things, you can figure out how to dial in those weights to give you the output that you want to have based on a set of inputs. And that's a very long process, and that's the learning process. Once you get those weights, the neural network can be executed really quickly. That's the inference stage, where you put something in, something pops out really quickly. And the problem with all the chats up until that point is they kind of had a certain sense of amnesia, or sometimes they couldn't even remember what the subject of a sentence was if you get to the end of a long sentence.
Right.
So you needed something to make sure it was like kind of paying attention to what was the important bits in there. So it seemed kind of scatterbrained and everything else. And that's what the transformers came in there, is to make sure it paid more attention to what was going on. And I thought that was like something that happened after the training, that, the transformers were to make it work a little bit better, and had absolutely nothing to do with the training set. And I think James Dalma kind of straightened me out on that a little bit, and you also, because I said, James, is this right? Because it sounds like the trend. I don't think Wolfram got it wrong. He doesn't get anything wrong. Okay, he knows what he's talking about. I was just like wondering if chat kind of did the summary wrong, because I think Bradford Ferguson already pointed out that it got the summary of the Tesla Q4 earnings wrong. It like came up with a number that's not the number. It was like way off.
Well, I just want to also point out that if people haven't seen the video, they should definitely check out our chat with ChatGPT, because it told us that it wouldn't lie, and then it lied, and then when we called it on it, it said, I lied about this.
Right. It makes some mistakes. It's rather amazing the amount of the knowledge that it has, that somehow it can cram things in. So one of the things that shocked me last week is that one of the founders of our company asked Chat to make a very simple poem about visual components in the style of Shakespeare. And it was brilliant. I mean, like, you might be able to say, did it get the iambic pentameter right, and a few other things, but basically it was in the right form, and most of the rhymes were right, and they worked out. But what was spot on was it was absolutely accurate. I mean, I know poetry is like kind of subject to interpretation here and there, but it really, it did not get anything wrong. It didn't add elements that weren't there. And we thought, wait a minute, the prompt was just visual components, and we thought it's not going to know who we are. We're just a smaller company. We've been around. There's so many other companies, and it could confuse us with someone else. but everything was in there, and we're just really looking at it and said, wow, that is pretty good. And then you start doing a bit more investigation, and then we asked, then with you, I showed it to you and said, what year
Right.
was Visual Components founded? And it said 2003. And I was like, no, that's wrong. It's 1999. So we know it doesn't get all the facts right, but sometimes it can be there. But then we found out, we started pushing it a bit more to tell us more about our products. It started to go a bit more in salesman mode, you know. It started like our software,
Well,
like
there you
the
go.
characteristics that weren't really there, and that. But I think what happens is it's lumped us in with like this whole field of simulation.
Right.
And when you
Right.
do that, you have like, wow, they're there, so they must do this. I think they do that. So it wasn't like it was intentionally lying. It
Right.
just has these fragments that it's pulling together that make sense. And that's why you have to be very careful. It can be so convincing
Right.
that if you have area level expertise, you need to go in there and make sure you're not
Yeah.
subject to that Gell-Mann effect that you go, well, he's completely wrong here. I know he's wrong. And then suddenly you accept everything else as gospel because it's not there. So you do need that check. And of course, I'm going off the rails here from what we're talking about, which is transformers.
No, 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 no. I
And
think this is
being able
actually, I think this is very valid.
okay.
This
Oh,
is a
okay.
valid entree into this
Okay.
because one of the things about this kind of large language model is it's going to be incredibly self-confident.
Yes.
It is a token, not even word, but token prediction mechanism. So what it's doing is there are, oh gosh, I can't remember. It's somewhere on the order of 40 or 50,000 tokens in I think in English specifically, but those are subwords. So something simple like walking would be walk plus ing. That's two tokens that make up the word. And then a more complicated word could have multiple tokens in it or something like that. And this is actually something that Google did years ago. And of course, they use this tokenization. So the reason why this is better than full words is because it's actually, by breaking it down, it actually makes it more accurate. And there's a smaller vocabulary, even though it sounds bigger to say 40 or 50,000. But if you look at English with all the medical terms and all of the terms of science and all of those other things, it gets way bigger. And then if you look at other languages on top of that, you have that multiplied for every language. So you can sort of abstract out the tokenization somewhat. And so it reduces it from the basically infinite amount of tokens you would have to have with all the languages in the world. So it is a reduction of that and it makes it more accurate. But the only thing this thing is doing is predicting the next token. So it's not even predicting a word. So if you put in, I am, and for whatever reason it thought walking was the next thing, it would then predict the term walk and then the term ing and then a space, the space token, and then down the street or something, right? So it would continue this on. So the insanely crazy thing about this is this model is not, it doesn't know anything. It's just predicting the next token in sequence as it goes. Now, the big thing that's different about transformers and large language models that have been trained on that is the window. And so I think what we can do is we can go backwards a step before transformers, which would be recurrent neural networks or LSTM.
You're right. And I think that's where I get confused because you said you expanded the window, and I thought the window is something that's happening after the fact and not necessarily in the training model, but it sounds like it's integral to the design of the neural net.
Yes. It's integral to,
yeah.
Yeah, go ahead. Yeah.
So this is where I think I also get confused, and we want to bring this in, is that one of the first things I then did after saying, oh, wow, I mean, it knows a little bit about us. I wonder how much it knows about our API. So we have an API to Python that we use in the software, which is an import. And you're just like, we have materials out there, but I can't believe it would have read enough for them because there's just so many other languages to learn. What would it know? And so I gave it a very simple prompt, and it came back, and it wasn't, it kind of got a little bit, but it was like way off the mark. And so I proudly posted it to our teams and said, our jobs are safe. Our jobs are safe. It's really bad. And then of course,
for now, just wait till GPT-4 comes out though.
He feeds it. He feeds it. So this is the same model. There hasn't been any change. He feeds it snippets of our help file.
Right.
And then asks it to come up with a complicated script for being able to take boxes off a conveyor and make a pallet pattern out of it. And it comes out and it's like, oh my God. It's like 95% right. We only found like one mistake. And so that's where I thought, oh, that's the transformer part, right? Because the whole idea is you have sort of this memory, which is recent memory, your short-term memory. But once your session is over with, it's kind of, we haven't retaught it. So when he fed the help file to it, it didn't reteach chat for the whole world anything about the VC
Right.
help file. It's just like, was that session kind of, and that's where I thought, oh, that's the transformer bit, right there. It's short-term memory. But now it
Right.
sounds like I'm
Right.
completely wrong. And it's nothing to do with
Mhm.
short-term memory. It has to do with a lot more. And something else is going on with the short-term. And then I'm going to ask you about that short-term memory and
Okay.
also FSD.
Okay. Yeah, these are all really good. So
Yes.
okay. So we do need to back this up to show what the state of the art was just prior to 2017 when transformers were
Mhm.
introduced. And transformers were originally introduced only for language models. They didn't realize how powerful it was going to be for everything, because spatial transformers were introduced about 2 years later in another paper called was attention is all you need, and
Mhm.
a picture paints 16 by 16 words or something like that.
Mhm.
Anyway, it was something along those lines. But anyway, so prior to this, you had recurrent neural networks, or RNNs, and LSTMs, which were long short-term memory. And for the purposes of this discussion, we'll just kind of lump them all together. But basically what you would do is, so let's just do it with words and not tokens, because it's easier to talk about it that way. But the cat sat in the hat or something, right? You're
Mhm.
trying to predict that. And the way that an RNN works is it gets then it gets to cat, it goes back and looks at that, and it says, like, what would the best next word be based on the and cat? And then maybe
Mhm.
it would be sat. And then it does that, and it looks back at the couple of previous ones, and then it says in, and then it looks back at the whole thing, and then it's probably a hat or something, right?
Mhm.
So it goes back and it looks at this, but it's a serial way of doing it. Every single thing is a time step.
Mhm.
I know that's kind of a weird way to put it, but every word is a point in time. And so it has to look back at the previous points
Yes.
of time.
Mhm.
And the way that neural networks work is that they use a gradient descent. Again, that
Yep.
there are other methodologies, but basically it's doing the chain rule of partial derivatives going backwards. In other words, for people who don't know what that is, it's doing math, and it's multiplying a whole bunch of numbers together to figure out how wrong everything is. So what you would do, of course, is give it a sentence like the cat sat in the hat, and you block off the words that are coming up, and it has to fill them in. And then when it gets it wrong, it's like, bad neural net. And so you multiply these numbers backwards through the whole
And that's the back
nested
propagation.
sequence. That's the
Yes.
back propagation.
Mhm.
Now, a couple of problems. Number one is this is serial, which means you can only ever do one thing at a time. It's always like this. Parallel is way better, obviously, because GPUs work better with that. You can parallelize things. But so the time element is a big, big deal for this. But beyond that, what happens is called the vanishing or exploding gradient problem. So what happens, Scott? You can tell me this one. When you multiply lots and lots and lots of numbers together in series, what tends to happen to them if you're not
Well,
careful?
if they're small numbers, they're going to just go to zero. If all the numbers are less than one, and at some point you're going to run out of precision on your computer, you're just going to suddenly, it's going to magically turn into zero,
Right.
because the computer has
Right.
finite amount of digits
Exactly.
that it can put in there.
Yeah. And then if the numbers tend to be more than one by any amount, basically.
Up by a lot, then suddenly it gets really big really quickly, and suddenly you get a floating point overflow that you suddenly run out of space. Yeah.
So this was the serious problem that existed before this. You had two problems. Number one, it was serial. So it was super slow, and you would never be able to parallelize this on a GPU. Because you could only run one thread at a time. And number two, the bigger problem, you're always having to play with renormalizing and balancing all of this stuff to try to get those exploding and vanishing gradients to disappear, so that you would get, you'd get reasonable error bars, basically, that would happen. And so the training process was a nightmare, and it didn't work particularly well. So there were a lot of problems. So what came along was this paper, and let me share my screen so we can get to that. And let's see here. It's actually going to go to the wrong page first, but I'll jump over here. Okay. So this paper came along on 6th December of 2017 from Google, and some folks at Toronto and everything like that. But I'm going to skip down. I'll leave this, of course, a link to this in the description for people who want to actually read the paper. It is an excellent paper, but this is the magic is what you get is you get a transformer type of network, which allows you, notice that the title of this is Attention is All You Need. So what happens is, if we go from the RNN, which is like everything looks back at the words before it within a given window, and just think like 8 words back, no big deal. But if you want to make this 100 words back, there's a lot of steps, and you're going to vanish or explode your gradient instantly. So the window was extremely short over what it could pay attention to. The whole beauty of transformers is that, given enough memory and everything, what you do is you lay out all of these words or tokens, as the case may be. You lay them all out and you feed them all in at once. So an entire window. So let's say you have 64 of these words or tokens, and you feed them all into this transformer at once. The transformer then goes through, the whole job of the transformer is to figure out what other tokens or words in that window you should be paying attention to. Right. And it can do this in parallel because all of this stuff is being shoved up at once. So as opposed to going like in a series, everything's in parallel, which of course for GPUs and stuff is the happy days for the GPUs. They're operating their happy days. Everything's good. So they can do things in parallel. And at the same time, you can look back 15, 20, 30 words or tokens, and you can say, oh, this is actually the thing I need to pay attention to. So, again, a simple sentence like the cat sat in the hat, when you get to when the cat sat in the, and it's predicting that next word of hat, it can look all the way back at cat. And it could say that's the most likely thing. And if it was something like the football sat in the, it probably would not predict. It would go back and it would know that, it needed to look at the word, the noun. In that sentence.
It has to pay attention to that. Yes. So the subject, predicate, everything we learned in grammar and school, and forget about.
Yeah, I mean,
sometimes
basically,
you go way over here to find out that this matches that and matches that.
It's it's not doing this explicitly, but in a way, it's kind of doing sentence diagramming, like that horrible thing that we have to do in middle school. So yeah, basically that's the situation that you're going. So you're going from in series and having an exploding gradient problem because you have to keep multiplying everything backwards to being in parallel, and everything only has to be kind of, all the gradients only really have to be dealt with in this little stacks that happen. So you don't have everything multiplying down the line and ending up with these huge problems. Now there are, let's see if they have, they have normalization here. So you can see like add and normalization. That is a step where they do have to do some normalization and stuff. And they also have to put input embeddings in. So apologies for the train out there, but an input embedding is it doesn't know, it's like a bag of words. So I don't know if you've ever done anything with artificial intelligence with bag of words before, but bag of words is like, so let's say you take the cat sat in the hat, just again, you just throw those all into a bag. So imagine like, what is that called? Scrabble. Right, where you have a bag and you mix up the letters, right?
Pull a word out.
Pulling out a word. It has no idea how they're related to each other. So you have to first do an input embedding step, which says, oh, this word is first, this word is second, this word is third in this particular sentence. So you do that you add this, the input embedding, sorry, that's the positional encoding, my bad.
Right.
I'm skipping ahead. So the input embedding turns the words into vectors. And that's been done before. That's art that people know about, word to vec and things like that. Sorry. Then you add the positional embedding, which they originally did with a sine wave curve, which is very cool. And that's, I think, why they use the sine figure there for that thingy. And then what you do is you do multi-headed attention. So you block off words. It has to predict the next word, but you don't just do it once. You actually create like maybe, again, I don't know, it depends on what model it is, but let's say you do 8 of these. So you have 8 different versions of the prediction of the next word. And then it can actually learn from that. And it's like, oh, this particular prediction did the best out of the group that we have here, things like that. You then go through a regular multi-layer perceptron, things like that, add normalization, and then you feed this into the output embedding. So the output embedding is the prediction of the next token that's going to pop up, which is your output probabilities. So again, neural networks are never going to give you a 100% confident thing, but what they might do is say 70% odds if you have the cat sat in that the next word is going to be hat, and then 30% in the bed, something like that is going to give you some probability setup. But basically, you're taking this input embedding and you're feeding it in after it's made this prediction. It's made an attempt to figure out what the next word is, and then you feed the word in and you say like, aha, this is, so you're giving it more information and it's training on this. So I feel like I'm doing a bad job. If people want to see a more like one that I thought a little bit more carefully beforehand, I did a whole video on this. So I go into this in more detail and step it out. I'm just kind of like off the cuffing this right now.
So if I sort of understand it, is that you'll first give it cat, and its attention will really be focused on that. But then as the sentence develops, the thing is the cat starts kind of going over here, and it kind of forgets that cat had anything to do with the sentence. And what you're trying to do is constantly pull it back in. And so the transformer kind of goes along and realizes, oh, these words here are not important, but this one is. And it will kind of always keep it as the center of attention, even much, much later on, because it might be the whole thing is a discussion about a cat.
Right.
And so it's like, oh, we want to keep our focus on that, and we don't worry about these other little details, keep on bringing it in. Some other details now are sort of important. Let's kind of keep that local into our memory. And then if we don't discuss that anymore, then maybe it just fades away and we pull something else in. Is that kind of what the idea of the transformer is doing?
That's more or less it. And when you look down at these pictures, you can see this. This is called a query key and value. So this is kind of like a dictionary. The key and the value are associated with each other. There's a value, which is what the meaning of the word or something like that. And then there's a key that associates it with that. And then you query it. So the query is the words that come before it, and you're like, what's the next word? And it goes through this basic matrix multiplication, figures all, dot products and all of this stuff. And it figures out the probability matrix of the next thing. But this all at the beginning is going to be random before it's trained. Yeah. It's going to give you garbage answers. But what you can do, of course, is it's masked self-attention. So basically, as you're doing the training, you have every sentence in English and whatever other language that you can grab off the internet. So one of the big advantages, of course, nowadays is that we have the internet. And so you can get literally trillions of words of data organized, right? This paper right here, you can read the text of that paper in, you can then throw it at this thing, and then you can just have it over the whole paper. It just runs a window where you're just saying, predict the next word based on the last 50 words, predicts the next word based on the last 100 words, whatever. So it has to go through that and figure it out. And if you do this over and over and over again on trillions of words, the numbers, because again, this is all just matrix multiplication in here, those numbers get really, really good at predicting the next word. But the kind of massive step change that this enabled was not just that, because a lot of that stuff is just basic to, even a multi-layer perceptron, the oldest kind of neural network thing, did that. But what happens is, as opposed to RNNs and LSTMs, your window goes from like 8 or 10 words to, I think people guess that ChatGPT has about 4,000 tokens of memory. So it has a window. So as you type in your questions, we did that whole interview with it, and we said, we could ask it. I remember, like, partway through that interview, I said, "What were the instructions at the beginning?" And it gave us that summary. It told us what it still remembered all of that.
And that's what I wonder is, like, where is that memory? Because when you bring it up, I guess there's no input. So does that mean like all the inputs are empty? And then I give it a few things, and now it has a few inputs, but it has all these other inputs that are empty.
Right.
And then as you're going along, you're starting to fill up those inputs, and does it jockey them around to realize that, well, I have some sort of short-term memory. I can only remember so much, but some tokens I'm just going to throw out, and these others I'm going to kind of keep as an input. So it won't be temporal anymore. It'll be more importance. So that is kind of how its short-term memory is formed, because once we leave it, everything is gone. It hasn't learned anything. The neural network has not been updated.
Okay, well, for our particular, like when we interact with it, it's just, if you want to liken this to full self-driving beta.
Yes, exactly.
When you drive down the street in full self-driviving beta, it never learns from you. It's not updating its weights, but the data that you give it can get shipped back to Tesla, and they can retrain on that.
And they have to go to Dojo, and they have to run it for a couple of months.
So, so your visual components thing, maybe if they're interested, they could pull that data. I mean, one of the brilliant things about ChatGPT existing online and people using it is it's learning all the freaking time, right? When it provides an answer and somebody says, no, you're absolutely wrong, that can get flagged and stuck back in the data set.
Okay, I guess it would that way if they send it back. But the reality is it's not like it's really retraining the network at that instant. It's that at some point they're going to collate all this stuff and decide, all right, we're going to do that. Because that brings me to full self-driving, because we can never finish a video without mentioning full self-driving, right?
Got to mention Tesla.
And that if you have like a transformer in full self-driving that seems to have some sort of memory or something, some sort of short-term memory, why can't that somehow be used to learn something about the local roads that I'm on?
Right.
And then, of course, eventually be able to store that and then load it back up the next time you're back. Is that something that's unrealistic?
It's not unrealistic, but I have a feeling it's incredibly unsafe. So let's just say that you had that capability, and whether through malicious intent or just stupidity, you taught it something bad. Like, let's just say you're let's say you're the worst driver in the world. So you're driving the wrong way down the street and you're doing donuts in the middle.
You're doing stuff like, but I think it could still put some sort of guardrails on there. What you're saying is that when I come to this intersection, this is when I prefer to move over to the left. This is around the time to do it. When you come with this other one, this is the lane that you need to be in. Right. You got to be a little bit careful. You always get over here. And so you think it would start to teach your routes in the preferred way. And of course, if you do something like that, it will just say, that's it. Sorry. I'm scrapping all that thing.
I mean, it goes back to that feeling of every time I get in my Tesla and it drives through my neighborhood, which it's done a lot of times now.
The first time every time.
It's first time every time. And so the advantage of having, even if it was just a navigation thing, because I always take a back road and it always wants to go on the main road, which has like 6 lights. And so I never take that route, which means I always have to disengage full self-driving at the beginning of every drive to take this back route around to avoid all these lights.
Right.
And it would be just, even if it could just memorize the navigation data, it doesn't have to do anything clever, just memorizing
something like that. And then maybe how you do it. And then if it starts to realize that this is your preference and it starts doing it a bunch of times, it starts honing in to realize that depending on the time of day or the different circumstances I've seen, this is the ideal way to approach that problem. And it will always solve that same problem the same way every time without actually having to send it back to the mothership. Because that would just be too much for the mothership to have to remember every single intersection in the world.
It's the same exact thing here. Okay. So let's just go back to the LLM, the ChatGPT thing. You've got visual components, your company. You put in information about this. I tested it with mine because my company didn't exist at the time they cut off the data. So it had a very generic-y answer about Artomatic, but it was pretty decent. I mean,
it knew Skinner, right? Didn't it come back and say Skinner?
Yeah, but I think I gave it that as part of the prompt. So I think it knew. That's the thing.
You rigged it.
Anyway, but the deal with these large language models is they're going to give you an aggregate training. The reason why I think people are blown away with ChatGPT as opposed to these older ones, which really sucked, right? The old chatbots, I've used them before, and they were terrible. They were a joke, but it was because the window was tiny. If you can remember a bunch of stuff and then, you, Scott, talk about visual components that say, write me a poem and all of these things. Well, someplace out there, it's gone and scanned your website and taken in all that information because it existed before 2021. And it even though it's not memorizing that in the sense of it doesn't have that in its memory, it does have associations. Remember the importance of different words. So when it gets when it gets the term visual components company or something like that, when it gets those 3 terms together, it's like, oh, this is related to these
and
things.
It associates it with things like digital factory and factory simulation, which it's learned from everywhere else. That's what I was saying. It's kind of bringing in that context there and making assumptions that, you must be able to do this and that. And then sometimes it's pretty good at those assumptions.
Exactly. So it's I'm not saying anything. I'm not knocking down the brilliance of this at all. I'm just saying it's a little bit more understandable where it's getting this from because it's got such a big, it's not a it's call it the working memory. I don't know, for people who are
Right,
neuroscience
right.
people, right? You've got your long-term memory, which is like your hard drive, and you've got your working memory, which is like the RAM of your computer. Well, these older language models, their RAM was like, 5 kilobytes or something. It was this tiny amount of stuff. And this thing then now is in the megabyte range of memory. And then GPT-4 could potentially, be an order
Be
of
even bigger, be even bigger. Yeah.
So we could be, instead of 4,000 tokens, we could be looking at tens of thousands of tokens.
Right.
And when you can do that, your working memory allows you to, again, it's only just multiplying weights out together. This is the reason why when people do these, they talk about suing these language models for like copy pasting everything.
It's not copy paste.
Like suing me or you, right? When you want to program something and you don't remember how to do a particular, you just go on Stack Overflow or someplace and you look it up and you're like, oh yeah, and then you type it. So would they sue you?
But it's not even doing that. It really is sort of vaguely remembering and figuring out what it's supposed to be without even consulting back to it.
Yeah.
So it doesn't have the advantage right now. Like, well, I'm going to look it up, because if it was really clever, when we asked the year that the visual components was established, it could have gone out and done a search, but it didn't. It had to pull it from its memories. And again, that's sort of how human memory works. Now, you, Fazard, and I had a conversation on Tuesday.
Yeah.
And
with ChatGPT?
Was it? Yeah, with ChatGPT. And even, was it Tuesday or was it Wednesday?
Even Wednesday.
Now I'm not. Okay, it was Wednesday. See, already my memory is fading on that. Now, at the time, I knew what day it was.
Right.
I knew the time of day that it happened. I knew the context, everything that was going on. That was all there. That was in my memory. It was all full. I had the context. But as soon as we left, and some of it started to get a little bit distant, and I'm trying to remember, I have a vague idea of what it was we talked about and some of the things that happened in there. But now you ask me a year from now, you remember that chat we had, and I'll think back, and then I might say, well, let's see. I think it was in the wintertime. Maybe it was in February. I won't be able to say it was.
Yeah, and you'll be like, who were the people with us?
And I do remember, and I'm going to think, was James there? I'm trying to remember. Wasn't he in that too? It's like, no, we wanted to. Oh yeah, that's right. Because it gets a little bit faded and fuzzy, and that's basically what's happening with ChatGPT. Is that when you're pulling that stuff in, it really has it there. But at some point, it's just going to have to fade. It goes into the background, and it becomes these echoes and impressions and shadows of what the truth is. And when you pull it out, it can be pretty convincing. So we do that all the time. I mean, I won't be able to pin down the year. I'll probably be pretty clear that it was like, it was cold. It was, I think it was when I was in Michigan. I think, I might not even get the location right.
Yeah. Well, I mean, this is something where a computer has it in spades over us humans. Yeah. That transfer of short-term working memory to long-term memory, we do a bad job at that. As soon as we go to sleep, all that stuff's gone, and we're
the way wake up the next our compression algorithm is horrible.
What did you have to eat a week ago?
Exactly. We don't even remember lunch. Let me.
Good God.
It was fish today. Okay. It was fish.
So, but we're just terrible at remembering things like that, whereas computers are really good at that. So anyway, I want to get to a philosophical point here, because I think it's a fascinating philosophical point that I really have become very intrigued about. Tom Scott, by the way, just did a video down in New Zealand where he said he's terrified of this because of the fact that it could program for him and everything. So anyway, but legally, unless they're going to sue every human being for reading the internet. So let's assume that we don't go to Stack Overflow, but you had gone to Stack Overflow and learned some coding thing, right? And then you remembered that and you used it. Are you going to get sued for that? No, that's crazy.
No. It's like, I mean, there's this old saying is that, if you copy from one person, it's called plagiarism. If you copy from many, it's called research,
Right, exactly.
So, right. Basically, it's just research.
Yeah. So it's going to be a very difficult legal hill to climb for content creators. And I believe me, as a content creator who's probably going to get disrupted in the next couple of years with videos, it's going to suck. But I don't know how you sue something for learning. It's basically doing research. That's what it does, and it's really good at it. But basically, just to go back to this point, the inference engine isn't learning anything. It's just multiplying all these weights together. The learning, the training part that's being done is able to be done across very, very, very many words or tokens, however you want to think about that, which then gives ChatGPT the kind of miraculous ability to pick, it can associate words that are really far apart from each other, an entire paragraph or something. And it can go like, oh yeah, that relates, take William Faulkner, for example. I actually tried a couple of William Faulkner. I said, write a summary of the latest congressional act in the form of William Faulkner. And it gave me these sentences that are like these massive sentences, but it can figure that out. It can figure out like the subject of the sentence and the adjective is way down here separated by 100 words. That seems magical to us, but it's because it just has this very large window because of the way that transformers work that it can find, and it's been trained an inordinate amount. I think that's one thing that human beings
don't realize,
understand is, like trillions of man hours of training. If you had human beings doing this, it would take probably the age of the universe or something. Not quite that much, but it'd be insane. So that's part of the whole thing that's going on with that. But then the really interesting thing to me, this is the philosophical part that I've become intrigued by, is what does this say about human intelligence? Are we just word predictors? Is that all we're doing? I mean, is that the same? Like, we're just really, really complicated, like word prediction, like large language models predicting the next tokens that come out.
It's in many ways. Remember the analogy is if you have enough monkeys with enough typewriters in a big enough room, they'll do all the works of Shakespeare. And that's basically the brute force. You just let them randomly do it.
Right.
And if you try to do that with the weights in your neural network, it will take you forever to get there. But instead, you've got back propagation going through there that is sort of making sure that when the monkeys type, they really are making words. Well, it's not quite as random.
You've got the million monkeys typing and the nuns who are hitting.
Which are going through and making sure they're getting it right. So, I mean, in a sense, we've got something up there that when it's random, we know exactly what the next word should be.
Right. Yeah.
Right. Everyone knew I was going to end my sentence with should be.
Right. So, I mean, it really does make you wonder. One of the things that's interesting about ChatGPT or anything like, or the image processing things, generators, is you have to prompt them. Yes. Like, even if it's just a random prompt, they need something. They can't start from scratch. So you could say that humans can at least prompt ourselves, but I don't know. There's kind of always an internal monologue happening.
The thing is, it just kind of proves that the neural network is just a form of chaos. Isn't that the whole idea of chaos, is that the system is so unstable, you just give it the slightest tweak one direction or another, and it just will just go off completely different. And that's, it's the whole idea of like the double pendulum, or even like holding a pendulum up like this, just slight change at starting condition and everything is different. Whereas in a linear system, the whole idea is that if I have a swinging pendulum like this, if I start here, it does something like this. If I just do a little bit, it does something so close that there's really no difference between it. But when you have a chaotic system, slight tweak in that input, and then the outputs can be very different. So that seems to be what's happening is with your prompts. And that's what I wanted to ask is there's two elements. I mean, one, the randomness of my prompt.
Right.
Then there are the weights and these functions that are going in there, which I assume when the inference engine goes through, does it always use them, or does it also kind of inject a little bit of randomness through the inference?
I have not heard anything about it using randomness.
Okay, so that is the same. In other words, if you give it exactly the same input, you'll get exactly the same output. And then the question is, well, why does Dall-E always do something different? And that's because there's another input to Dall-E, and that is the white noise that it starts with. Yeah. And so basically, it's amazing that you just give it an image that's just noise, and the noise is different each time. And if you give it the same prompt, it will then go through and develop a different image. Where the whole idea, it's like you look out at the sky and you look at the clouds in the sky, what do you see? And then you are just developing your whole image based on what you see, and then it keeps on going the next level, the next level. So it's that noisy image that you put in. And that just kind of shows the nature of kind of chaos. If you took that same image and maybe just change one pixel, the whole thing will be different. It won't be like close. It won't be close.
Let's try. Okay, I'm going to do a new chat very different. What do you want the prompt to be? Because I'm going to ask it to do 2 new chats and give it the exact same prompt. Tell me a story about the cat in the hat.
Sure.
Story about a cat in a hat. So let's just, so I'm going to, if I start a new chat, it should hopefully like regenerate from scratch. So it'll be interesting to see whether this is identical or not. So, okay, it doesn't really matter, but mischievous cat named Whiskers.
Now, do you have to restart it again? Because if you
What
put
I'm
it in
going
the
to do
same
is
one, it's now got the context.
I'm going to force it to do a new chat. So that should reset it to be
right.
And then we can, okay. I should have told it to write me a short story about Whiskers. So,
so I would think that, maybe the weights they don't have any random, because there was those sigmoid functions, right? And do the sigmoid functions have any random nature to them?
No,
or do you think they just have a couple of inputs that they're randomized? Like they just take a timestamp?
Yeah, I mean, neural networks are deterministic. So I'm starting a new chat. I'm going to paste in the exact same thing. Oh no, it's different. Absolutely.
Yeah, it's very different. It's very different. But so they're very deterministic. I mean, it did start,
okay, mischievous cat named Whiskers who love to wear hats. It does have hats, which is interesting.
Right. Well, it should, because you asked it about a cat in a hat. No. Yeah.
Oh, now it's mad at me because But anyway, we can see that it was definitely generating a different. It was definitely different.
It was it was definitely different. But I'm wondering is that as you go down that list of words to pick,
right?
You have a list of highly ranked words, and you can always go with the one that has the highest rank, or you can decide, well, I'll just dealer's choice, choose what you want, and that would give you this different avenue of randomness. Right. And that's what I'm wondering if that's what's happening inside the neural network, is that when it gets to that point that I have to pick this one or that one, now let's just go ahead and flip a coin.
Yeah.
Or roll one of those hexagonal die or whatever it is.
Right. Interesting. This actually goes to a red listed thing. There, I was, what was the conversation? I can't remember who the people were, but they were talking about, it was a computer file. They were talking about red listed and green listed words to try to make it obvious when something like ChatGPT was being utilized for a research paper or something. And the idea was to subtly push your finger on the scales to make it a little less or a little more likely to pick some words, so that then statistically, if you give it 2,000 words, it can look at it and go like, nope, definitely generated by ChatGPT, because you can see that it's doing this thing. But so maybe what's going on here is that they are introducing some random noise into it. So you give it the prompt, and let's say that the cat named Whiskers, I think it was the cat named and then a cat, mischievous cat, something like that. But that there's a 52% probability that mischievous is the next word, a 40% probability it's cat, and then some other random stuff. And what it could do is it could take the top 2 or 3 possibilities and randomly choose one of those. So maybe it's injecting randomness through that.
Okay, and does that mean if
it's still a probable, it's still the probable word that's coming up next, but not absolute?
If they're putting kind of their finger on the scale or doing that, does that mean they're in a way kind of watermarking the output?
Well, that's been the whole question, is whether, and this is really interesting, because this means if your biology teacher in high school gave you a prompt and you copied it and pasted it into ChatGPT, it looks to me like you would not get the same paper as
you'll get the same one every time, right? Every student would get a different one. Absolutely.
Right, which makes it incredibly difficult to defeat this.
So you can't do the plagiarism on that.
Yeah.
The only way you do it is that you then say, okay, submit a paper, and then you bring the students in and you ask them about the paper they wrote. And if they can't answer questions about their own paper, they didn't write it. Right. As simple as that.
So,
or at least they didn't even bother reading it.
But this is where that paper that they were talking about in computer file is interesting, because if you could, without it even being visible, subtly weight this, so that he was talking about a random seed. So what you'd have to do is know the seed. But let's say you started with 42 as your seed, and that after that it would always generate the weightings to subtly push one word above another one constantly throughout the whole thing.
Right.
You could replicate that and see the process and see that it was definitely generated by ChatGPT as opposed to a human, because it was almost entirely green, whereas a human would write 50% green words and 50% red words.
Right. And now it can write in the style of Faulkner and Shakespeare and E.E. Cummings or whoever you want it to be.
Right.
I imagine you could end up taking examples of your own writing and putting it in there, and then learn your style to make sure that whatever produces is in your style.
Right.
That might be the way to defeat it, is that if you would take samples of a lot of the, a student has to give you a corpus of their data of everything that they've done.
Right.
ChatGPT learns that, and then you compare it against it and say, what are the chances that this is in his voice, their voice? Okay. And then you were going to know right away. It's like, no way they did it. That's kind of how chess.com works, is that a person's rating, and if suddenly they become super good overnight, there's something wrong. It's like, yeah, they can get to there, but they have to kind of go up this way.
Like this.
And so we know, we're hoping they don't always write like this. That's the whole idea of the English classes, is to up their game. But their game is not going to suddenly do this overnight.
Right.
So now it could, and this is what I think it's really good, is if you give examples of writing essays and you get exposed to those things, it is going to up your game.
Yeah.
Because that's the whole thing, is that they say in order to become a better writer, you need to be a better reader. The more you read, the better you're going to do it. So if you get more examples of how to take a prompt like that and then look at all those different samples that come out and read those things and study those things, you will become a much better writer. So I really do think that this should be seen as a tool that will actually help students become better authors.
Right.
Not that they're going to be better cheaters. There's probably going to be some way to be able to find out if they can cheat. But they definitely, chess.com, I think, is producing a lot of pretty good chess players.
Yeah.
And it's because they get the chance to do it. It's not creating more cheaters. It's actually, I think, in balance, is creating better players.
Right. And that's the hope. And I think the other thing is, just like when calculators came around, you had to change the paradigm of grading, because when we were kids, I definitely remember this, and I'm sure you do too.
Yeah.
Multiplication tables, doing things like long division and all of this crap that's just unnecessary anymore. We got graded heavily on that stuff. That was
you were being tested on arithmetic. You were not being tested on mathematics.
Exactly.
In the end, what we want is someone who's a good mathematician. We really don't care if they're good at arithmetic.
Well, but again, if you dial it back to the 40s and 50s and 60s, you actually did want people who are good at arithmetic, because
they were the computers.
They had to be computers. They had to be the human computers that would do the work. So but that's not necessary anymore. So it's the really same sort of situation here, where the sort of drudge act of writing, which is very tedious, eventually, I don't know what English classes are going to do, but it's going to become more about the ideas that people have and less about the drudgery of writing, where these will become tools where you can produce.
And remember, the main thing we had to learn is how to spell words.
Oh, gosh,
all the time, vocabulary and all this other stuff, and examples, and then getting your grammar right and making sure there's no mistakes. And now it's like, Word is like, taking all that out. The kids aren't going to learn how to spell. It's like,
actually, I'm way better at spelling than I was as a kid, because it's always correcting me.
It's always great. I'm seeing, that's what's wrong. Oh, okay. To this day, I still cannot spell architect. And I've given it like 35 prompts. What's the right way? It's like, one of these days I'm going to absolutely learn, but
as long as you get close, ARCH.
Close, yes.
So, yeah. But so, I think this is a technology. Wow, we've really gone all over the place. But I think that for educators, this is a technology you're going to have to embrace. You can't fight it. The only thing you can do is fight. If you're going to die on the hill of having people not use this at all, you're going to lose. There are going to be ways because people are going to come up with the ChatGPT defeat mechanism, which will change the paper enough so that you can't detect it with ChatGPT anymore, right? Something like that.
Yeah. So. And they get points for cleverness. Sometimes it's like, okay, they know how to because that's a form of learning as well. And I'm sure there was a controversy when the slide rules first came out. Oh, it's good. Yeah. Kids don't learn how to multiply anymore.
They're just going to do this. So, yeah. All right. So we've talked. So going back to the transformer issue, has this random conversation we've had, has that helped you to understand why
a lot?
Transformative?
I understand. Yes, I understood why they were important. I just didn't understand where they fit in the architecture. I thought it was like a post-processing thing. I didn't realize it was so important at the very beginning and integral to the beginning of what's going on.
It is the architecture. It's the middle part. It's the meat of the sandwich, not the bread.
Right. And the other thing is, if you want to make jokes about someone's, being very forgetful, you just say that, they need to upgrade their transformer, right?
Right. Or you could say upgrade from your RNN to a transformer architecture.
To a transformer, yes, maybe, yeah.
Because again, I mean, transformers and LSTMs are just gone. Nobody pays attention to them anymore. And a lot of computer scientists, had careers about that stuff.
Yeah.
They were very important stepping stone, but now they're just like, nobody cares because.
But is there a parameter for the transformer to say, make my transformer this big? Or is it like, if you go to that architecture, that's just what it is?
No, you can stack these on top of each other.
Okay, so you can limit the size of a transformer. You can say, I only want it that big.
Yeah, what we were looking at in those pictures were kind of blocks, and you can stack the blocks on top of each other.
Okay.
So you can make them very deep, but of course, again, with the expense of computation time gets incredible, and you need incredible amounts of data. The big downside of transformers is you need insane amounts of data to train them. Which, going back to full self-driving, guess who has millions and millions of miles of full self-driving data? So you need that, because the first thing that you have to do, so you can fine tune these models, but you have to do what's called just kind of unconstrained training. You just throw everything at it. You're like, here's 1 trillion words of English, process this, and go off and spend a month and $5 million of Microsoft's cloud, Azure computers. Spend that amount of time just learning the basics. Once it does that, then you can, if you're OpenAI, if you were actually OpenAI, you could give this to people, the actual neural network.
Right.
Because the magic,
that's right.
The secret sauce is just all those little floating 174 billion floating point numbers. That's the secret sauce. Nothing else. It's just that.
Yeah, that's true.
Yeah. Anyway,
okay. So
we are.
I guess it's time for everyone to enjoy their weekend finally.
Yeah, there we go. So I think this is going to come out on Sunday if I've got it right. But anyway, so everyone can be enjoying their weekend and geeking out with us about all of this stuff. But anyway, whenever it comes out, I hope everybody enjoys this. And Scott, thank you so much, because we did 2 videos at once. So it's been quite a while. So watch both of them, robotics one and this one. They're awesome.
Yep.
Cool. All right, everybody have a great weekend. And whenever you watch this, have a great day. Bye-bye.
Yep. Cheers.